I'm going to talk about the contribution of push-up work gait acceleration. To maintain steady gait walking, you need to compensate the heel strike loss, collision loss, colored as a green bar, to maintain the same speed. One possible candidate could be the toe-up push-up during the double support phase, and the other one will be the hip torque during the single support phase. Among many other combinations of these two candidates, collision compensation purely by the push-up it was employed for steady gait trials, and the simple biomechanical analysis showed that that's most energy efficient gait. So in this study, we want to first examine is the dominance of push-up is still hold for the acceleration trials, and also the observed strategy has anything to do with the energy efficiency. So we collected over-the-ground gait trials for steady walking and accelerated gait, and for accelerated gait from stand to walk up to their maximum gait speed, the subject shows their own acceleration. Ground reaction force data and the velocity data showed consistent gait acceleration throughout the trials. And compared to the steady state gait trials work shown to your left, you won't see any significant difference for the collision loss, while we have a significant increase of energy input that needs to compensate the collision loss and speed of your gait speed. And different from what we expected from the steady gait trials, acceleration trials doesn't really have a big increase for the push-ups. Rather, we have a significant increase of the single support work. Why do they have a different strategy employed for the acceleration? To answer this question, we calculated the mechanical work done produced by each gait phase and calculated the optimal push-up that minimizes the energy. The simulation shows that as you push harder and harder, your push-up work increases in a quadratic manner as a function of push, while it decreases the heel strike loss as a function of push. And for the case of steady gait trials, which means the acceleration rho defined as a speed increase per step normalized by your initial collision velocity, shows the complementary behavior is a function of push-up work. So for example, for this line, you have the amount of push-up colored as a blue line is lacks the collision loss colored as a green dashed line. So to compensate the energy, which is a red line, you should have a complementary single support work during, by the hip torque, which colored as a purple line. So with respect to the zero crossing point, the left-hand side means that your push-up lacks the collision loss, so additional work should be done during the single support phase. For the right-hand side, that means you have excessive push-up during the double support phase, so you need to slow down during the single support phase by applying negative work, which is unlikely energy efficient. So if we define the optimal push-up as the push-up, the amount of push-up that minimizes the total work input, as far as you don't have non-negative push-up work, this point marked as a star as a least costly gait is that's what we observed for the steady gait trials. But if you walk faster and faster, if you accelerate your gait, those optimal push-up increase with the function of acceleration ratio. And for example, rho equals 0.2 means you have about 20% of gait increase per step, means you gotta really push hard, which means most of your energy for acceleration should be provided by large push-up. As opposed to the model prediction of minimal cost, as I showed you before, the data show that rather than having a great push-up, it has most of the work done during the single support phase. Why is it different from the model prediction? What should we consider more? So if you look at this star line, which means the optimal push-up as a function of gait acceleration, it means that it has a monotonic increase, which means if you want to increase about 20% of your gait speed per step, you need to almost double your push-up force, which means you need to have a plantar flexor torque. Therefore, we think that maybe this observed strategy change might to accommodate the biomechanical constraints on your feasible angle torque. Therefore, we would conclude that for human movement, energy really matters as far as you observe the biomechanical constraint. And for a simple collision model, we're able to approximate the energetic related to the human gait acceleration. I'd like to thank my grad students, especially Keonyoung. Most of the work done by him for his master thesis work, and we have a poster. Thank you.
Thank you very much. Let's go for questions. Yes, please.
My question is, was this work implemented on a robot, and could you indeed show that the push-off was reducing the impact?
Could you please say it again? Sorry.
Okay. The study you made, I didn't quite get it. It's a pure model.
I didn't quite get it. It's a pure model or a model and robot study. And if it was implemented on a robot, could you show that the push-off did indeed reduce the impact?
Sorry, there's somebody who clarifies it. The question was, if I implement it for the robot study, do I expect to see the reduced push-off?
You haven't implemented it on a robot.
No. I haven't implemented it for the robot. I just did it for the human study and trying to analyze it, why the strategy change happened, and then conclude that it's not for the energy minimum strategy. Rather, you need to observe, you can't really push hard. That's your physiological limit.
This is a simple question. It seems like you should get identical results for walking uphill at constant speed. Or almost. This may be a simpler way to do the same experiment.
Yeah. Well, physiologically, if you're going to the uphill, you need to overcome those gravity part. But since we don't have the treadmill with the incline, with the force plate built in, costs a lot of money. So we'd rather let the people walk faster and faster.
You're simulating slopes by acceleration.
Oh yeah, I can do that. Yeah, because for this specific setup, because subjects have their own acceleration ratio, we cannot really examine the different road. But yeah, that's good trial. That I can really check it later. Thank you.
Art?
I guess two things. One is I'm curious what happens to the collisions during this, because it seems to me that it doesn't matter what combination of push-off and single support work you do, as long as you reduce collisions. Theoretically, you can reduce collisions to zero. Let's say you do some work during single support, and then you do some work in double support, so as to produce zero collisions.
Well, if you have a minimal costly, like energy, minimal least costly gait, you will just keep having a reduced collision because we have a greater push-offs that's actually changed the momentum, so your heel strike doesn't really do work. However, what we really found was you didn't really change much from the steady state gait. You have a decent amount of push-up collision work and the heel strike collision loss and the push-up work. So theoretically, for minimum costs like this, but you still need to observe the biomechanical constraints, so you can't really do that.
Right, but I guess I'd still like to see what happens to the collision work, not just the positive work.
You mean the amount of the collision work?
The amount of negative work in the collision.
Well, the net sum is shown here like a green bar, but we haven't really specified the each, even though you have a full setup. I'll check that out later. Thank you.
Okay, and then the second thing is we found that a lot of the positive work that's done for push-off sort of starts before double support. So we like to break things down, not in terms of single support, double support now.
Yeah, that's what I do like this.
Producing positive work.
Okay, what you said is rather than just specify the space as a double support versus a single support, I should also expand it as they say maybe velocity switch up or something like that. Yeah, we haven't done it yet, but that's definitely also the thing that I need to work on.
All right, thank you so much.